layers and the dense layer. So we are now subsequently moving towards the end of designing CNN, where we try to conclude it with flattened layers and dense layers. So we are going to see what exactly it is. So in the flattened layer, so the flattened layer is a component which is used in the neural network architecture, particularly in deep learning frameworks like the TensorFlow and Keras. So now what is happening here is, the purpose of this flattened layer is, what do you get exactly as an output from convolved layers after pooling is, and probably dropout also, is like a feature map. So it is like a matrix, correct? So you have it in the form of a 2-dimensional or a 3-dimensional array. Okay, so now what are we going to do here is, it is necessary that whenever you are going for a transition from a CNN, you already know what is the purpose for CNN, right? So CNN was basically used for image like data. So a normal ANN could not resolve properly working with that humongous images as the data, because the number of pixels that it had and the data it carried was way too broad for it to serve. But what we are doing inside a CNN is, first we are using convolutional layers along with other layers like pooling and dropout, etc. To downsample it, and then you are adding this convolution layer to an ANN network only later. Okay, so it's like an ANN is prefixed with certain layers before, and then the result becomes like a CNN, correct? So now what exactly do you require as an ANN? You require ANN data to be as a vector as an input. Okay, it can't undertake array data like a 2D or a 3D array data, just that gets you, that is the output out of the convolutional layers. Okay, so before it actually applies to a fully connected network like an artificial neural network, you require this feature map that you obtain out of CNN to be resolved and look like a vector. Okay, it should look like a one-dimensional array. So the purpose of transforming this feature map data, that is the resultant out of convolutional layers or the pooled layers, and to convert that into a one-dimensional array, you require to use a flattened layer. So flattened layer is used just before the dense layer. Dense layer means your fully connected network or your simple artificial neural network. Okay, so you have to use a flattened layer just before you use it to a dense layer. So it is often used when transitioning from a CNN to fully connected layers that are also known as dense layers inside a neural network. So that's how you are going to use a flattened layer. Next is moving to dense layer. The other name is fully connected layer also, and we all know it's a fundamental building block in a neural network. So now what happens is, in a fully connected layer, you have each and every I'm sorry, you have each and every neuron. See, if one layer has got certain neurons and another layer has got certain number of neurons, each neuron is connected to every other neuron in the other subsequent layers. There is no dropout as such. Okay, so that's how the name is dense, and the name is also called as fully connected layer. It's gonna connect each neuron from one layer into every neuron in the next layer, thereby creating a densely connected network. Now you already know that all of these neurons which are present in this layer have got their associated weights W. Apart from that, every neuron is going to, every layer is going to have its own bias. So every neuron in that layer will have their associated weights and bias that are coming. Okay, so the number of neurons, apart from the neuron, you also have these associated parameters, I mean to say, weights and biases. So now what do you do after every layer when you want to apply non-linearity to this? You already know, right? I have been talking. If this layer it is summation of Wx plus B. X is input, W is associated weights, and B is the bias, correct? But this is a linear network. To impart non-linearity, at the end of this, we are going to apply an activation function. We have been reading this so long. So a nonlinear activation function is typically applied at the output of each and every neuron inside a dense layer. It's just like a simple ANN that we have discussed so far. Okay, so there's nothing special about dense layer. So the number of neurons in the dense layer is going to determine the output size of the layer, and the output size is nothing but a hyperparameter which is going to depend on the task and the architecture of the neural network. So based on what type of output you require, you are going to decide about how many number of neurons you are going to put inside your dense layer. I hope you are clear with this. Now, sorry. Now, let us take a typical example wherein, as now we have studied now a proper convolution network, right? So what did we study so far in a convolution network? You always have got an input, then you have convolutional layers, you have pooling layer, you have dropout layer if it is an overfitted model, and then once you have got this, you will be using a flattened layer to convert this feature map into a one-dimensional vector. Then you will be using a dense network, and then you are going to have your output. So this is basically the strategy that we go for designing a CNN model. So let's now take up a basic exercise, a simple hands-on exercise on a very basic convolution neural network. I'm going to use here an MNIST data set for simplicity, and it consists of a grayscale images of handwritten digits of 0 to 9. And the CNN architecture is typically going to constitute of convolutional layers followed by pooling layer. Here I have chosen a max pooling as a strategy, and I am also going to use dense layers or fully connected layer. This particular model is trained using ADAM as an optimizer. You can also try this with an SGD, stochastic gradient descent optimizer, and go for it. Because it is a typical classification, I am choosing loss function as a categorical cross entropy. And after the training, the model will be evaluated on the test set. Okay. So that's our basic strategy of what we are going to see. So let's quickly see how does it look like. So let's design it. One second. So I'm going to design it for you. So this I have already coded here, and I think if it is visible to you. So I just first wrote a simple code wherein I have divided my MNIST. I actually downloaded, or I mean it is an automated data set present inside TensorFlow Keras. So I loaded it and divided it into training set and test set. And after that, what I did is I normalized this particular data, and I wrote a function in order to display 16 of this data set, 16 images out of this data set, so that you get an idea how exactly it looks like. So you can see here it is like a handwritten digit. So we are going to give a particular classification for this. So this piece of code was just written for you to understand how does an MNIST data set looks like. So this is how an MNIST data set looks like. Okay. So this is like 16 4 by 4, 16 images that I have extracted. Now I begin coding for my CNN. Okay, and what I do is I first import my libraries. That is, here I am importing NumPy. I am also importing a sequential network wherein I want to create a sequential model, and the layers that I want to impart in this, they are convolutional two-dimensional layers. Max pooling is what I have chosen, flattening layer, and a dense layer or a fully connected layer. Correct? Now data set is MNIST, so I am importing it, and I am going to go for a categorical classification. So I decided it, and I have taken my data set and preprocessed it as training and test data set. I normalized my data set. Why? Because 255, say I have divided it because it's a float 32, and I want the pixel values to be in the range of 0 to 1, mostly because it's a black and white images is what I have seen. That's why I am normalizing the pixels to be between 0 and 1, and I one hot encoded my labels so that I can get a category from 0 to 9. Okay. I added a channel dimension because I am using it as a convolution layer, so I require it. So once I have done with all these prerequisites, what I am going to do is I am going to build my CNN model. So this is exactly what is my CNN model, and I am building a model, sequential model, and to that I am going to keeping on, because sequential container you have heard in Keras, right? The beauty of it is you can add and delete any n number of layers that you want as per your model type. Thus I called an empty sequential container, and then I am adding a convolutional 2D layers. You can see how I have used the kernel size, how I have used the activation function as in ReLU, and what is the input shape that I have, I am passing it on. So this is my first layer. So how is my strategy? Conv layer followed by a pooling. Once you have convolved, you have to downsample it. So immediately follow it up with pooling. Unless and until you find this particular model as overfitted, I frankly tell you, don't introduce a dropout. If you are thinking that it will be an overfitted model, or you got your training accuracy and testing accuracy aligning as such, telling it is an overfitted model, when both of them tells you that training accuracy is good but it is failing in testing, then it is an overfitted model. Then you have every choice to put up a regularization technique like a dropout. Okay, until then I am not choosing it. So I am using a first convolution layer, and then after that, as I told you, I have to choose the size of my pooling to downsample it, and I'm choosing a 2 by 2 pool. Second layer of convolution. Now you can see what is this, the size I am increasing it a bit. Okay, and then because as I told you, you subsequently go on extracting more and more features, so you can increase the size of your um, convolution layers over here, the number of the dimension of your convolution layer. Kernel size I have kept again fixed of 3 by 3. Again, immediately after that, I am applying a pooling layer, and again I am using a convolution layer. So I feel for my model of such shape of input, I am good to go with 3 layers of convolution. Based on the accuracy, you can increase or decrease your convolution layer, that does not matter. Now once I am done with my convolutional layer designing, I find that now I can go on and conclude my model. So immediately I go for a flatten layer as discussed. And always remember, convolution layer should be pooled, should be paired with a pooling layer. Okay, for smaller thing where you think that the dimension is good enough, you don't require to down so sample it further, then okay, you can skip it. But then initial stages it's always good if you pair pooling layer with convolution, and then at the last you decide based on your dimension where you want to downsample or not. So here I have not chosen any pooling layer. So it's again designer option, whoever is developing this particular code based on typical application, you can choose. Okay, and then once you have got a flattened layer, you get a one dimensional vector, you are free to choose your fully connected layers or dense layers. So you can see here I have chosen my dense layer because I have got my size here 64. So here I'm beginning with 64 neurons in my dense layer, and my activation function for every neuron I'm going to use ReLU. And last I am going for my output layer. So my output layer will also be my dense layer, but I have to be very specific with the size here. Since I am having 10 as an output, 10 outputs I have got from 0 to 9 as my category. So I have chosen here size as 10. Suppose if you are going for binary classification, you better give it as 2. Okay, so output size, you please be careful while you are as per your application demands. So here I have 10 classes, so I have chosen here size as 10, and definitely my activation function here is going to be softmax. Had it been a binary classification, I would have used either tan H or ReLU again, but since it is multi-category classification, I have chosen here softmax. Once I have built my CNN model, I am supposed to compile it, give a suitable optimizer. Here I am choosing Adam. You can try and use SGD for yourself and check for accuracy. And I am using here categorical cross entropy because it is multi-category classification, and the metric that I am going to test for is accuracy of this model. Now I fit this model for training purpose, wherein I have to give my training data and I have to suitably fit the number of epochs. See, again I am telling you, number of epochs and all, you have to, it is again user specific. If you find your validation accuracy, your training accuracy needs more improvement, and if you want to see if by increasing the number of epochs, if you see the accuracy is increasing, then you better increase the number of epochs and check for yourself. And if you are using going for a batch size gradient descent operation, then in what batch you want to go for, you are free to select it. I have chosen it randomly, and I have chosen epochs as 5, and as a validation data I am giving my test inputs and outputs. Now I evaluate my particular model with respect to test accuracy, and I am going to print my test accuracy. Now you see that once I do that, if you can see onto the screen, for my first epoch my accuracy was 87%, which was about for my training accuracy, and validation accuracy was 98 accuracy. Not bad, both training and validation, they are coming good. And at the end of 5th epoch, after it has run, I got my training accuracy as around 99%, and testing accuracy is 98.8, which I think very good for this particular model. So I'm not going to further move with any of the other things. I'm not going to change my optimizer. I'm not going to change my number of epochs. I'm not going to introduce any dropout because I don't think the model is overfitted. So I think yes, this is a very wonderful, very small basic CNN model that you can go for it. I would like to you people to work on this particular model and do it for different types of optimizers. Check if you're getting any overfitting condition, you can include a dropout. And second is, write a piece of a code wherein you can give an input from this MNIST data set, one of the image, and check whether you get a correct output or not. That I leave it as a task for you. So this was about a simple CNN model.